Well, good evening. Welcome everyone. As Matt and I just said, this is a talk on Introduction to Sound Localization. Those of you unfamiliar with the term, sound localization is the process of determining the position of a sound source by using the streams of recorded audio data. So in this talk, we'll be discussing some of the methods commonly used to do this, and some of the applications that these kind of techniques have. We're covering some algorithms based on time cues, first of all correlation algorithms, and then looking at a slight alternative to them with spatial gradients approach. Then I'll be looking at some more biologically inspired methods, finally giving a comparison based on complexity, the spatial limitations of each of these, and the accuracy in practice, and then look at some applications and alternative methods that I don't have enough time to properly discuss. So the first set of methods we're going to be looking at are correlation algorithms. For these, we'll be using the setup shown here. We'll be having two microphones, one at position M1 and one at M2, and there'll be a single source of sound at an unknown position P relative to the microphones, such that the sound approaches them at an angle alpha. And our goal here is to identify this angle, and with these methods we'll be trying to do that by using the interaural time delay between the two microphones, which we'll define specifically as being the time between a wavefront of sound hitting M1 and it hitting M2. So for example, here we'd see that wavefronts hit M2 first, so this value will be negative. It's just something to bear in mind if you're going through the maths in your head in a minute. So for these algorithms, we'll be assuming that the distance between the microphones and the sound source is much greater than the aperture of the apparatus. For this, this is so that we can model the sound as it approaches as a plane wave, and thus the angle at which it approaches the microphones is constant. We'll be using the interaural time delay to calculate alpha using this equation here. Once we've found the delay value, we can just rearrange and solve. And T sub D max is the maximum possible time delay, which quite clearly occurs when your sound source is in line with your two microphones. So correlation is just a simple property of two continuous functions. Here we'll instantiate it for x1 and x2, which are signals from the two microphones respectively, using some offset parameter tau, which will be our estimate of the time difference. By observing the composition of the signals from the two microphones, we can see that they consist of the true signal S, which is what we actually want to observe from the proper source, and some noise signal, which for the purpose of this discussion we'll assume is negligible, and any that does come up is they are independent of one another and of the original signal, such that their correlation turns out to be 0. So with that in mind, our equation for correlation becomes what it is on the bottom, from which it is quite clear to see that this will have a maximum value when tau equals the actual true delay. So the cross-correlation algorithm just takes a discrete time approach to this, and that is literally the conversion that we did to get from this equation to here. This gives us some value y corresponding to the correlation at the number of samples of estimate delay I, and using by maximizing y, we can then find the value of I which does this, and use that to calculate our estimate of time delay and hence alpha. So this method is a good start. We can obtain sufficiently accurate results using a single bit of quantization from our microphones, which means rather than the standard floating point value between -1 and 1, each sample of our input stream is either 0 or 1. We can do this because the approach of correlation relies on time-based cues rather than of actual relative amplitudes of the two signals. Using this one-bit quantization, it makes our instructions a lot simpler, and to the point where this can efficiently be generated within hardware. In order to use this effectively and to get a high precision from this method, you need to use a high sampling rate for your audio. For example, if you were to use the standard 44.1 kilohertz sampling rate, and let's say your microphones are about 20 centimeters apart, this means that the maximum delay between them will only be about 21 samples, which means you can only identify 21 different regions of space. By increasing the sampling rate, you reduce the size of these regions, and hence you have more, and your precision improves. This algorithm relies on finding a maximum point. For that, you can use any maximum finding algorithms you'd like, but by making a small adjustment to the equation, we can make that a lot easier. So the cross-correlation derivative algorithm is just a slight improvement on this by noticing that a maximum in y is a 0 point in its first derivative with a negative value in its second. We can just find an estimation for the first derivative and find where that goes from a positive value to a negative value. With this, we can still use single-bit quantization, and actually with that, this summation here becomes effectively a simple up-down counter for which you can just use a single min term of the 3 signal terms there for each up and down. With that approach, it means that you have no need for expensive multiplication circuitry. You have very low circuit activity, which obviously consumes a lot less power. So it's a really good thing to use if you're needing to do this for a mobile application. I've created a small simulation of these correlation algorithms, which I'll just demonstrate to you here. So we'll start by generating some tone, which we believe came from our microphones. Won't add any noise because we assumed there isn't any. Then we shall simulate it coming from some other position. So this first diagram here is a top-down view of the apparatus, with the thing in the middle being where our microphones are, and the blue thing where we have our source. So if we put it out at some distance and say want it about azimuthal angle of about, is that 60 degrees? Yeah, close enough. Apply that, and if we were to zoom in, we can hopefully quite clearly see that the right audio is somewhat ahead of the left audio because of where the microphones now are of where the source now is in relation to the microphones. So if we were to now use the correlation algorithms, we can see that we get a reasonable approximation to this. Apart from the minus 90. Ignore that. Besides that, we got some reasonably good estimations of the azimuth angle. And in fact, the difference between these is pretty much exactly one of those bands I was speaking of before, because this is done at the standard sampling rate. That's the kind of accuracy you're looking at. So the alternative to the correlation algorithms, sticking with time-based ones, is generally the spatial gradients approach. For this, we'll be using 4 microphones arranged at the corners of a square. For this method, rather than looking at the time delay just between 2, we have to generalize it to a time delay of tau of r, which we define now to be the time delay between the center of the apparatus and some relative point r. By expanding this signal term in a Taylor expansion, we get that. Taking this to first order in our delay for each of our signals, we get these equations here. We can note that because of the shape of our apparatus, we have the same delay between microphone 1 and the center and microphone 2, and similarly for microphones 3 and 4. So we can just relabel these as constant parameters tau 1 and tau 2. By taking combinations of these equations, we can isolate these different delay values, put them in terms of our original signals and the derivative of s, which we can calculate using this approximation. In practice, this approximation does amplify some of the effects of high-frequency noise, but as we assumed the noise is negligible, that should be perfectly fine to use. These current equations for the delays technically only consider a single sample of your audio data at a time. So that's a very unreliable approach. We want to be sampling over more. So by constructing some vectors over a frame of n+1 samples, we can then use a least mean squares approach to finding our values and then using these to solve alpha. Just by taking their, from here you can take their ratio and you get tan of alpha inverse tan, you find it. So these have been very good methods that have come from understanding the physics of the situation, but nature has been working on this problem for a lot longer than we have. So a lot of people thought, why not look to see what nature has done, observe what happens with actual humans. So it turns out with humans, we have very well-designed ears, heads, and torsos, such that they actually apply a physical filtering to the sound before it reaches the inner ear, and the filtering is highly dependent on the angle at which the sound approaches the body. So this effect can be modeled by a finite impulse response filter H, which is the head-related transfer function. And the signal that is received by the microphone, R, is just the original signal sent by the source convolved with this transfer function. This model here in particular is called a KEMAR head. It's just something that's used in industry a lot for identifying these head-related transfer functions. And if you see any particular research about the field, they'll almost certainly be using them. It's just a point of interest. So first such algorithm that will be making use of this is the inverse algorithm. Considering that we have two streams of input data with different transfer functions applied, we need to try and find some way of making sense of both of them. So why not apply the inverse filter and to try and get back the original signal? That will only work if our inverses are for the same angles of the transfer function. So we can use that as a method of testing our estimates of the angles. And indeed, this does work. The equation on the bottom is what you would actually use to solve it. But in practice, this isn't very good because these inverses are very difficult to calculate. The transfer functions are very complex functions. They involve both time cues and frequency-based effects. So it's very difficult to get an exact inverse for them. And so it's computationally expensive to actually create them. You may think, well, we'll just do it once, store the functions, and then reuse them on the fly when we need to. That's okay, but in order to get any real accuracy from these inverses, they need to be about 3 times the size of the original filter. And so that makes our convolution operations a lot more expensive, and ideally we'd just like to not be using the inverses at all for that reason. So the cross-channel algorithm doesn't use inverses. Instead, because we can actually measure these transfer functions, we just apply the one for the other ear or the other microphone, and that way, by the symmetry of convolution, we have that both of our signals should now be identical if we applied it for the right angle. We can now optimize this for our estimate angles and hopefully use that to find the correct angle of approach of the sound. How does this compare to the time-based ones? Well, if we look at their complexity, how difficult it is to implement them, the correlation-based algorithms, as you can tell by the fact that I was able to do it, are very easy to implement, and as I mentioned earlier, can even be done built into hardware. The spatial gradients approach takes slightly more complicated equations, but the main point is they have no optimization step. There's no searching for these turning points. So it's always a fixed calculation, and so it should be done in you should get a better estimate for the amount of time it takes, which is always a nice property for your algorithms to have. The transfer function-based techniques will actually take a similar amount of time for each estimate angle to test as the correlation algorithms, but because the functions are very complex, their shapes may not have a distinct maximum or minimum in them, and we're optimizing over 2 variables. The optimization step takes a lot more iterations, so it actually takes quite a bit longer to actually do a run of the algorithm. Not all of these can actually, in the way I describe them, give you an exact value for, let's say, the whole field of solutions that the source could lie in. For example, using 2 microphones for the correlation algorithms, we can only determine those things in the plane in front of us. Because there are loads of places in reality that will give the exact same time delay between 2 points. Those lie on a cone extending from the center of the apparatus. Obviously, if you have 2 things on opposite sides of this cone, the angles are completely different with respect to the actual microphones. So, but this algorithm would give the exact same values. However, by adding more microphones and repeating it with each pair, we can overlay these cones and reduce our our solution space. So by adding a 3rd microphone, we reduce it to 2 lines that the source could lie on, one above the plane and one below. And by adding a 4th one outside the plane, we can reduce that to a single line with relative confidence. Similarly, spatial gradients approach works well in the plane, but it gives no sense of elevation. So solution is, again, add more microphones, make them outside the plane, and just repeat it with each plane you have, and try and get to the best fit of them. This is the area where the transfer functions really come to their own, because using just 2 microphones, you can have an understanding of where it is within the whole 3D environment. However, it's not necessarily full 3D in a way, because as we found out with a lot of studies of transfer functions, the effects between, difference in effects between front and back are very subtle, and so we do still get front-back reversals. In experiments, this was found to occur about 5% of the time, which is still pretty good, but it could be better. And speaking of statistics, let's look at the accuracy. So in an experiment done by Julian et al. In 2004, the correlation algorithms were tested, and with sources in the plane in front of them, they were able to determine the position of their source within less than a degree of error, which is very, very impressive. The spatial gradients approach was tested in the same experiment and had the same accuracy, but the spread of the estimates for a given source position were much more reliable. So it actually works a bit better. And the transfer function-based ones were tested in a separate experiment in 2006 by McDonald and Tran, and they were found to have specifically the cross-channel algorithm was found to have an error of about 2 degrees, which is obviously worse than 1 degree, but it's still far more accurate than typical human hearing, which has been found to, at best, be around 5 degrees of error. However, these aren't technically better ways of doing it than having a genuine person at the scene, because none of these can really handle noise. With everything I've said today, all of the assumptions have been noise is negligible and noise is uncorrelated to one another and to the signal. But in reality, those are very difficult things to come by. Noise can can be internal noise within the microphones, can be other sound sources, and it can even be echoes from the original sound source. So literally any surface will give you an echo, whether it's walls, floors, ceilings, other objects around you. They will cause delayed versions of the original signal, which will screw up correlation calculations and generally introduce error into your results. So these are by no means ideal solutions, but they do occasionally work. And you may still be thinking, well, where are these actually still appropriate? So a lot of the research has been driven by the idea of using these in unmanned vehicles and drones, because at the moment, a lot of them are guided by a single camera and being able to tell events happening within that space. But a camera has a very narrow, fixed field of view. By using by using speakers, we can get a full, we can respond to stimuli all around the machine. And by sound localization, we get an idea of this sound vision with which the unmanned vehicle or drone can react to interesting events going on all around them. And in particular, it will help with military vehicles with targeting and things like that, if that's apparently good. Humanoid robotics are intended on being integrated with society. They're humanoid because we want to be able to accept them as humans. They want to be able to react to things as humans do. And in order to do that, they need to be able to simulate all of human senses, which includes having an idea of sound localization. So it is almost essential for those purposes. When people have impaired hearing, they often find that their sense of sound localization is dulled slightly. They lose track of some of the regions. They may not be able to tell between front and back very well, or up and down very well. So all of the knowledge we've gained through studying these sound localization methods can be used in designing hearing aids and such to either emphasize the cues that humans listen out for when determining the origin of sound, or we can create new cues and teach people how to spot them, such that we can give people with impaired hearing another sense of sound localization. A lot of you may have come to the talk today thinking, identifying where things are with sound. That sounds like sonar. Yes, sonar does do that, but it's been in a completely different way. Active sonar uses a technique called beamforming, which is where you have an array of speakers positioned such that the interference from their signals is constructive in a very fine region. So all of the power is concentrated in a fine beam, and we know that whatever response we get from that area came from a particular angle. And we do the same kind of structure with microphones so that we can filter out down to a specific region, and then using the standard sonar distance equations for determining the distance to that point. So it's quite different to the algorithms that we have described here, but it's just another way of understanding where things are using sound. The image on the right is an artist's impression of the cochlea, which is a small part of your inner ear. And the grey tube-like thing that's running through the image is the basilar membrane. That is a membrane which the sound is sent along and has varying thicknesses and stiffnesses across its length. In humans, it allows us to change the way in which frequencies are amplified across its length, so we can so the hairs in the cochlea can listen out for particular frequencies. But in the stereosis approach, which is another sound localization technique, we can use an artificial basilar membrane because the way the sound travels along as a traveling wave, we can use that to simulate the time delays we need for correlation algorithms rather than using, let's say, shift registers or maintaining a buffer of things, which again assists with making a hardware implementation of everything. And there's also been some quite interesting recent research into neural networks for sound localization, even more closely modeling how we as humans determine the origin of sound source. So for instance, you'd have an input from different frequency bands for each ear. Those would then go into some layers which would apply some neural filtering to the sounds in addition to the physical filterings that have already occurred. And then each of those would filter into coincidence detection regions. You'd have one of these regions for each kind of spatial environment spanning a few degrees of space around the person. And the coincidence detection region which spikes the most is the one that's assumed to be corresponding to where your sound source is. So that's more how humans are doing it. And these models are starting to be put into practice with computer science. But the accuracy of them isn't quite as good as the algorithms I've shown here today just yet. But if you're interested in the subject, that's where I reckon a lot of the research will be going in the next few years. So it's quite an exciting thing to be involved in. This discussion concludes the talk on sound localization. I'd like to open up to any questions.